Question 17. A student drops a paper ball from a balcony 4.00 metre high. Her friend measures the time taken for the paper ball to reach the ground. Part A. Suggest the equipment used to measure the height of the balcony and the time taken for the paper ball to reach the ground. This question is about experimental technique, so we just need to demonstrate that we know which tools are best for whatever we're trying to measure. So for height, we could use a ruler. However, they have told us that it's quite a large height, so a standard ruler, such as the one I'm using here for the exam, won't cut it. It'll have to at least be a meter ruler for it to be appropriate. Alternatively, a tape measure would do even better. So in hindsight, I recommend a tape measure over a meter ruler. A ruler by itself is going to be really tedious, especially if it's 4 meters. So avoid that trap. Time taken is slightly easier. We just need some kind of watch or a stop clock. So I'll put stop clock here. Question 17b. They record their results in a table. Here's the table. Use the data in the table to calculate the mean, median, and mode of their results. A little bit of maths here. Fair enough. The mean is essentially the average. So we add all the data together, then divide it with 5, since there are 5 different readings. Mean equals all of this added together. Stick it into the calculator. 2 seconds. Which seems about right, seeing they're all round about 2 seconds. Some above and some below. However, in calculating this, you'll notice that while some of the results are very close to the mean, one of them is pretty far out. As this is a higher tier paper, we need to show good scientific experimental skills, so identifying that anomaly is crucial. Here it is. Let's discount it and recalculate the mean, 2.04. You'll be pleased to hear that the mark scheme allows you to have 2 seconds as your mean if you forget to discount the anomaly. With that in mind, I'll show you the 2 different ways of answering this question. The median would be the result, which is in the middle if you order the results from smallest to highest. So let's do that quickly now. 1.84, 1.98, 2.02, 2.08, 2.08. Without discounting the anomaly, our median is really easy to find. It's literally the one in the middle. If we have accounted for the anomaly, the median is slightly tricky, seeing as the mark scheme is a bit weird on this. If we've removed our anomaly, these are the numbers that make up our data set. So our median should be here, also known as halfway between our 2 middle numbers. Or rather, the mean of our 2 middle numbers. The mean of our 2 middle numbers is 2.05. However, the mark scheme says allow 2.06. I can only assume that they've inserted their mean of 2.04 into this data set and then found the halfway mark between 2.06. But even that doesn't make sense. Anyway, last to find out is the mode, and the mode is the one that appears most often. Luckily, we've got 2 bits of data here which are the same, and that's the same mode regardless of whether or not we dealt with that anomaly. Before we move on, I just want to point out that either of these methods, one where you account for the anomaly and ignore it, or the method where you leave the anomaly in and keep calculating, both of these methods are acceptable so long as you've shown some working out. And I'm pretty sure if you line up your numbers like this and show you're working for the median, giving you 2.05, the examiner will look at that and be like, oh yeah, and allow you to have that mark. Question 17b, part 2. The results are not very precise. Explain how you can tell from the data in the table. Well, we were talking quite a bit about this anomaly earlier. There's quite a spread of results, so that's going to be our answer here. The data has a wide range, so 1.84 all the way to 2.08. The mark scheme will also allow you to say that the results aren't particularly close together, but avoid saying that the results are not consistent, because this is quite an ambiguous term. So data has a wide range. Question 17b, part 3. Suggest a possible source of error in the experimental method and how it could be improved. Now, error is all about how the scientist will use the equipment to get the data. So we should have a look back at part A, where we have our measuring of height and measuring of time taken. This is where our error is going to come from. With that in mind, I'll split up my answer into 2 sections. There are 2 ways to answer this. One to do with measuring the height and one to do with measuring the time. So for height, our error could be not measuring an exact height. You could also mention parallax error when you're reading the ruler. Our improvement here would be a clear indication of where to drop from. Otherwise, our source of error could be in the timing, and I feel that this is the easier way to answer this question. The source of error would be reaction time, or starting and stopping timer correctly with the ball. And the way we can get around this would be to maybe video the drop and use the timings from the recording. Alternatively, we can use a light gate. Now, like I said, I think the error and the improvement is easier to talk about with the timing. However, I don't particularly like the improvements that the mark scheme suggests, because we end up changing the method. We're no longer using our stop clock, which we mentioned up here, whereas our improvement for measuring the height is still using our meter ruler or our tape measure or whatever, but we're changing the way we're using it. So this is actually a better improvement of a method because we're using the same equipment, whereas I don't like the idea of improving a method by changing the equipment altogether. But that's just my opinion.